Hello, my name is Sven Lilge and I am a PhD candidate at the Continuum Robotics Lab at the University of Toronto. In this video, I am presenting our recent work on the kinetostatic modeling of tendon-driven parallel continuum robots, which has been published in IEEE Transactions on Robotics. Continuum robots are mostly characterized by their small form factor, inherent flexibility and compliance, as well as their ability to conform to highly nonlinear shapes and trajectories in 3D space. Envisioned application areas see continuum robots working in confined and cluttered environments with limited access, such as minimal invasive surgery or industrial in situ inspection and repair. However, there remain some challenges arising from the inherent characteristics of continuum robots that make it difficult to realize the envisioned application areas, such as their limited stiffness, low accuracy, and slow operation speed. To this end, parallel continuum robots, or short PCR, have been proposed which aim to find a compromise between the compactness and dexterity of continuum robots and the strength and accuracy of parallel robots. One common design approach sees multiple coupled continuum links in parallel assemblies, which are actuated by displacing their proximal ends, while deformations occur passively due to coupling and external forces. Other PCR designs utilize additional actuation principles to actively bend or elongate the shape of each continuum link, leading to additional controlled deformations. Here, commonly used actuation principles mainly include pneumatics, hydraulics, shape memory alloys, and tendons. Our work is focused on tendon-driven parallel continuum robots. These architectures feature multiple individual tendon-driven continuum robots in parallel arrangements, while coupled to a common end effector. Here, prior work mainly focused on the design and modeling of these architectures. The majority of previous investigations are focused on planar designs, utilizing simplified kinematic models, while some more recent work features some preliminary results for the design and modeling of spatial structures. This work extends the current state of the art by introducing an exhaustive fundamental framework for tendon-driven PCR that allows to model the kinematics and statics of spatial manipulators. It additionally allows for an in-depth characterization and analysis of such structures, serving as a basis for future research concerned with the design and control of tendon-driven PCR. The proposed kinetostatic modeling approach relates the robot's actuation Q and external loads W to the resulting end effector post-TEE and the shape of each individual robot X. The shape of each individual tendon-driven robot is described and modeled using Cosrod-Rod theory. The resulting modeling equations for each manipulator consist of a set of differential equations that describe its state along its length. This state consists of the position and orientation of the robot center line and its strain variables, describing its local deformation with respect to bending, torsion, shear, and elongation. Constraint and boundary conditions for the differential equations resulting from the parallel setup are derived. These mainly include geometric loop closure constraints of the parallel assembly, as well as static equilibrium equations derived using Newtonian mechanics. By considering different variables as known and unknown, the constraint equations can be solved to compute both the inverse and forward kinetostatic problems. The derived modeling equations are solved using a shooting method whose procedure is outlined here. We start with taking an initial guess for our unknown variables depending on the problem we want to solve and using them to integrate the Cosrod-Rod equations for each individual tendon-driven continuum robot as an initial value problem. We then evaluate the constraint and boundary conditions of our system and check if the residual is below a predefined threshold. If this is the case, we have solved the kinetostatic problem. Otherwise, we are computing the Jacobian of our constraint equations with respect to the unknown variables. Using this Jacobian matrix, we can update the unknown variables in order to converge closer to a solution that satisfies the equations of our system, before starting a new iteration of our optimization routine. Evaluations on a physical prototype show that a calibrated model can predict the deformations of the robot well. This video shows a side-by-side view of the physical robot and a simulation based on our proposed model. Overall, a median position accuracy of 4.9 mm and a median orientation accuracy of 6.4 degrees at the end effector could be achieved. The model can be computed in less than 100 milliseconds, allowing for update rates of 10 Hz and higher. The derived kinetostatic model can further be utilized to gain insights about the robot's kinematic and static properties. It can, for instance, be used to generate manipulability and compliance ellipsoids, indicating the motion capabilities and stiffness properties of the robot in specific configurations. It can further be used to detect singularities of the robot. In this example, the occurrences of type 2 singularities are highlighted. These singularities indicate that uncontrolled and unstable motions of the robot's end effector are possible, even though the actuators remain locked. This essentially means that the robot loses the ability to withstand loads in certain directions, as indicated by the compliance ellipsoid in such a configuration. In conclusion, we have developed a fundamental framework for the modeling and characterization of tendon-driven PCR. We envision that this framework will be invaluable for future work on the control or design synthesis of these structures, which ultimately will bring tendon-driven parallel continuum robots closer to their envisioned applications. Here, we particularly envision scenarios in which each continuum robot can first be treated individually before coupling into a parallel assembly to collaboratively work together.